ARUNACHALAM. Today I am going to take the topic fundamentals of vibration. It is the one portion which is related with the finite element analysis. So in this vibration we are going to discuss on the basis of finite element analysis point of view. So as usual, what is meant by vibration? Vibration may be called as oscillation, or otherwise we may call it as periodic motion. So from the word periodic motion, a motion which repeats something within a period. That means any motion which repeats itself after an interval of time is called as vibration. It has other names, oscillation or periodic motion. Actually, the vibration has is available or which occurs in all the bodies and the structures, because all the bodies and structures they have mass and elasticity, and they are capable of producing the vibration. So the vibration which forms or which causes only the basic phenomena of the mass and the elasticity. So that normally in vibration they are saying it as spring mass system. They may say, for a calculation point of view or some shortcut point of view, they may say it as a spring mass system. So as usual, spring which consists of elasticity and as usual mass. So the basic and very important factors behind the vibration is mass and elasticity. Say the spring mass system. Consider the diagram. Just go through with the diagram. Here your one end, the upper end is fixed, and we are having the spring. At the end of the spring you are having a mass. So the initial stage is position A. Here we are segregating it as a B, C. So the initial stage is A. So at this position A, one end of the spring is fixed, another one end of the spring is connected with the mass. At a particular time it is prolongs at a equilibrium position. That means that is the position A. Now you are applying some force, or due to some its own weight, self weight of the body. What happens? The position A, the mass of the body at position A, which moves vertically downward to the position of the point B. That is the extreme position which is reached by the mass. Why it was happened? How it was happened? Due to the strain energy, the mass reaches at the position B, and after that it the spring which reacts with its elasticity. So the mass at the position B which brings back into the another one upper extreme position at the position C. So these two phenomena at the position B and at the position C, they had the kinetic energy is converted into potential energy or the strain energy. In the equilibrium position, we are having the potential energy or the strain energy is converted as a kinetic energy. So that is the spring mass system, which was very important in your vibration. And another very important topic: what are the causes? What are the roots of creating the vibration? So nearly we are having some 6 points are there. So unbalanced force which has occurred in the machine. So whenever the machine is rotating or the machine is oscillating, whenever there is a rotating or oscillating motion, there should be unbalanced forces are there. Once the unbalanced force which creates in the machine, then that causes the vibration. And another one is the elastic nature. Of course, every body has a elastic nature. So while we are giving any kind of force or the load that reacts, that makes the vibration. For an example, if you are going to simply knocking the door, or you are simply giving the for just a force on a table, so automatically the elastic nature which reacts, that makes the vibration. And what about the self-excitation? That self-excitation which causes the vibration, that means the dry friction between the two mating surfaces that makes the self-excitation. For example, if you are simply what's that? You are making your both hands, just make it as a some more motion parallel to each surface, though that makes a self-excitation. And the external excitation. So that's that the external excitation means that is force. That means if you are playing the musical instrument, the guitar, drums, which are maybe that. So at that time, the musician, he plucks the chord of the instrument. For an example, if the guitar is going to be played, means the string is going to be disturbed by the hand, by the plug. So that is the external, the additional force which was available away from the body, which makes the body into vibration. So that is the external excitation. Another one is, as usual, we have the blowing wind. That means the electrical transmission line and the cell phone towers, that makes the great the vibration due to this wind. Of course, the another one, the great disaster, that is the earthquake. So that earthquake which makes the huge and very within a short period, which makes a very huge damage, isn't it? So that's these are all the causes of vibration. And next one is, what are the effects of vibration? So here we are having both sides, both positive and negative sides are there. So let us see what are all the negatives. Usually the vibration is considered as a negative one. Of course, existence of vibration in any mechanical system which produces the unwanted noise, high stress, poor reliability, and premature failure of one or more of the parts. While the meantime, if we are having a great source of human discomfort in the form of physical and mental strain. If the vibration is continuing in any kind of system, means the human being, he is not comfort, he or she is not comfort with this. For an example, if the person is traveling in a car or in a vehicle, so automatically he will, if the vibration is created in that vehicle, means what will happen, the it is a some discomfort, isn't it? So that's why it is a negative point, negative effect which is made by the vibration. And what about the positive effects? Yes, in spite of the bad effects, the vibration system are built in machines. Why? Almost all the musical instruments, vibrating conveyors, vibrating screens, shakers, stress relievers are the basic applications. That is a positive applications for the vibration. Especially another one is there, that shaker or the demolisher. Okay, so that is a huge application for the construction people. It was used by the construction people. So there's some positive effects are there, but most probably vibration is not good for a system. Okay. Okay, so it is not good for a system, so that we have to eliminate or reduce the vibration. How can we reduce or eliminate? There are many kind of ways are there. So let us see. First one, remove the cause of vibration. So just to find out how the vibration is created. So just to, if we find out the reason, it will be easy to eliminate it or reduce the vibration. And if we in a proper mounting, proper cushioning, proper seating, maybe furnished for the machineries or the structures, means that will be a great vibration reduction. And another one is by using the shock absorbers, we may eliminate the, or we may reduce the vibration by using the screens. For an example, some vibration which forms a unwanted noise, so that noise is always some more very disturbance to the human being, but it should not be avoided, means then for such a cases we may make a screen, whether it may be a very glass or fiber screen like that. For an example, in some of the CNC machine you may see that, okay, it was covered by the cover, right? So that's why they are saying it as a, using the screen we are reducing the vibration. And another one important thing is, that is the terminology of vibration. So these are all those things are very keenly watched and should be kept in our mind throughout the lifetime. What's that? A periodic motion. a motion which repeats itself after a particular interval of time. That is the periodic motion. What is by time period? Time period is denoted by TP. Time taken by a motion to repeat itself. Also, it is known as a period of vibration. It is when it has a unit of seconds. And another one is cycle. What is that cycle? Motion completed during one time period. Yeah, motion completed during one time period, right? So time within one time period, how the motion is going to be taken. And another one is a frequency, that is number of cycles completed in 1 second. Okay, so closely watch it. What is cycle? Motion completed during a one time period. What is frequency? Number of cycles completed in a 1 second, that is denoted by hertz. What's that? Natural frequency, the frequency of free vibration of the system. If a body, even in the world, every body has its own frequency, that is called as natural frequency. What is that? Amplitude. Yes, that is the very important thing. That is a very important thing. That is maximum displacement of a vibrating body from the mean position. Okay, so the measures is known as amplitude. It is denoted by x. What's that? Resonance. In a body, in every body they have its own frequency, that is called as natural frequency. If we are going to disturb, or if we are going to apply the external force, or if we are going to apply a force on the body, while the meantime the external force is having the frequency and the same body is having the natural frequency. Once the external force frequency and the natural frequency of the body both are all going to be equal, then that causes the resonance. During that time period, the amplitude becomes excessively large, so that just consider, just keep one thing, or just remind one thing. During the travel in our vehicle during the rainy season, if you are playing, if we are playing the musical system in the vehicle, we should open the all the windows in a very little bit gap, because during that particular period, if you are in a closed vehicle, if you are playing the music, so at a particular period of that time, the natural frequency of the glasses and the natural frequency and the external frequency, that is our music, both frequency going to be get matched each other, so automatically the damage will be causes. So in many of the cinema we may see, especially in a Tamil film, that is in Indian, one film is there, so in that film also one of the scene is there, right? So that is called as resonance. Okay, and another one is the damping. It is the resistance to the motion of a body, right? It's a resistance to the motion of your vibrating body, so that is called as damping. That is why we are giving a resistance for a vibrating body. Example, we may say it as a rubber pad, shock absorber, are those things. And a very important phenomena how this vibration is going to be simple harmonic motion, something it was related with our mm, um, sinusoidal wave. Yes, of course. Why this sinusoidal curve and the simple harmonic motion are matched each other? There is a great and basic thing is there. Let us see in vibration point of view. A body vibrates about a mean position. Okay, so here you are having the mean position. Okay, that was inserted by yellow in the figure, and such that its acceleration is always proportional to its distance from the mean position and is directed towards the mean position or the equilibrium. So let's see what in the mid of the line we are having the mean position. So first capital X, that means our amplitude. If we are applying the load, what will happen? The spring which elongates, so or some any one thing, okay, any one kind of vibrating component. So what will happen from the O, that particular amplitude is in moves in the positive x direction. Okay, so in the positive x direction. Okay, right. And another here, again it was getting down, and here it reaches the maximum period. So here it is a minus x and here it is a plus x. So that's why they are saying it as a mean position. This, so it is continuously repeating. It is continuously repeating throughout the sustaining of the vibration. So actually the sine curve is also in the same concept. The sine curve is also in the same concept. So here both the curves are following the same. That means in a mean position, the both the distance are going to be same. That's why SHM which follows, or SHM curve is also looks like a sine curve. So that they are saying it as a sinusoidal curve, right? Why? The basic thing is here, the in the mean position, okay, in the mean position, from the mean position it is moving so towards a positive amplitude, while the meantime it is also moving into the negative. The both the amplitude in positive direction and the negative direction, both are all the same, which cross, it should cross over the, which should cross over the mean position. So that's why it is comes under the category of simple harmonic motion. That's why it follows the sinusoidal wave, right? So equation of this SHM, which is purely excused for our betterment, for simple harmonic motion for vibration, d square x by dt square plus omega square x is equal to 0, right? Okay, so as usual you are having some other formulas are there. Time period is equal to 2 pi by omega, and the frequency f is equal to, very simple is there, reciprocal of time period is our frequency. So frequency f is equal to 1 by tp, that means omega by 2 pi. So just keep any one formula in your mind, my dears. So frequency f is equal to omega by 2 pi, that is a very important thing, right? And my dears, another very important area, that is the types of vibration. So what are the types of vibration? So here we are having many types of vibration. Initially we may categorize it by two. How? The vibration according to the actuating force, only the applying, based upon the applying force it was categorized. Another one is according to the stress in the supporting medium. Okay, so first, according to the actuating force, the vibration is categorized by two types: free vibration or natural vibration. Another one is the forced vibration. Okay, so free vibration, another one is the forced vibration, and mm, another one is free vibration is again categorized by damped free vibration, undamped free vibration. Forced vibration is again categorized by damped forced vibration, undamped forced vibration. And of course, the vibration according to the stresses in the supporting medium, it is categorized by three types. Already you know about that: longitudinal vibration, transverse vibration, and torsional vibration. My dears, in finite element analysis, the vibration is going to be discussed only along with this longitudinal vibration, transverse vibration, and torsional vibration. We are not concentrating on the forced, especially damped free vibration, undamped free vibration. Okay, so we are only concentrating on the stresses in the supporting medium. That means longitudinal vibration, transverse vibration, and torsional vibration. So let us see the basics. What is by free vibration? If the periodic motion continues after the cause of original disturbance is removed, then the body is said to be under free or natural vibration. Example: oscillation of a simple pendulum. Already you know about, very familiar about those things. Forced vibration, when the body vibrates under the influence of external force. Simply we are hitting, or simply we are disturbing a body by an external force. By what's that? By applying the force using the hammer. So that's the logic. So then the body is said to be under forced vibration. Example: machine tools, electric bells, conveyors. And what is in by damped vibration? When there is a reduction in amplitude over every cycle of vibration, the motion is said to be damped vibration. It is categorized by free damped vibration, free forced damped vibration. So now next one is according to the motion of the system, the types of vibration is going to be categorized. So here, good, longitudinal vibration, transverse vibration, and torsional vibration. So longitudinal vibration, if you are applying the force along the axis the body which moves along the axis. Okay, so parallel to the axis. So those kind of vibrations are called as longitudinal vibration. So another one is the transverse vibration. So here the vibration which occurs merely perpendicular to the axis of the body. Okay, and the third one is the torsional vibration. Here the vibration which occurs at the which rotates about the axis of the body, so that forms the torsional vibration. Okay, so longitudinal vibration, the vibration which causes along the axis or parallel to the axis, and the transverse vibration, the vibration which forms or which produces by the merely perpendicular motion, which merely perpendicular to the axis, that the transverse vibration will be occurred. And if the body is rotating based upon the axis, that means we are making the angular momentum, that forms the torsional vibration. So my dears, up to that we had some basic things related with our vibration, and here we go with some problems, especially some solved problems are there, which are all purely related with our finite element analysis. And here we are currently concentrating on the types of motion of vibrations, that means longitudinal, torsional, and transverse vibration. So here when first we are seeing about the longitudinal vibration. So question is, find the natural frequency of longitudinal vibration of the unconstrained bar as in figure. So just concentrate the word unconstrained bar. That means the boundary condition is not given, whether which one is fixed. Okay, so that they are saying it as that word. So whenever you are go through with the problem, just concentrate the conditions, boundary conditions clearly. So we are having a two different cross section of the bar, especially element 1, element 2, both are but fortunately both are having a same length, but unfortunately we are having different cross sectional area. So element 1 is having 2a and element 2 is having a as cross sectional area. So given in this problem, two different cross section of the rod was given, so both elements have different material property. Element 1 it has an area 1 to a, and L1 element 2 it has a area A2, length L2, and Young's moduluses are both common for each other, and density are same for each other, mass density. And here we have to find the natural frequency of the rod. So very simple thing. So whenever you are going to start this kind of problem, first we have to keep the stiffness matrix of the bar element in our mind. Already we have a familiar with that. So K is equal to AE by L into 1 minus 1 minus 1 1. So we are applying for the element 1, so that it is changed as K1 is equal to A1 E1 by L1 into 1 minus 1 minus 1 1. So here for element 1, A1 is the area for the element 1, so it is given as a 2A, so that A1 is replaced as 2A, and E1 is replaced as E, and L1 is replaced as L by 2. So by solving those things, finally the K1 is equal to 2AE by L into 2 minus 2 minus 2 2. Why here we are making this kind of 2 is simply at the outside of the matrix, but here we are having, we simply commonly taken this 2, right? Why? Because if you are going to assemble two different element stiffness matrices, then the constant value should be it should be same, then only we will easy to assemble the remaining stiffness matrices. So let us see in the next slide. So here K1 is equal to 2AE by L into 2 minus 2 minus 2 2, right? Just go through this here. Similarly for stiffness matrix for element 2, K2 is equal to A2 E2 by L2 into 1 minus 1 minus 1 1, as usual formula. So here we are applying the A2 as A, E2 as E, and L2 as L by 2, because these three values are already given in the problem. So now our final value is K2 is equal to 2AE by L. So just to see there, here K1 is equal to 2AE by L. Here K2 is equal to 2AE by L. So that here this one is going to be splitted as like this, because for assembling purpose we should have a constant value as the same, then only it is very easy to assemble these values. So now very important thing for especially for vibration, here we have to additionally we have to keep another one important matrix, that is mass matrix, especially for bar element. So mass matrix for mass matrix for element 1, m1 is equal to rho al by 6, that means rho 1 a1 l1 by 6 into 2112. So as usual we are applying all those values. So rho 1 is replaced as rho, a1 is replaced as 2a, l1 is replaced as l by 2, because these three values are already given. So we got the values m1 is equal to rho al by 12 into 4221, right? 4224, right? Next one is similarly for m2 rho al by 2 into, we very important thing is we have to, whenever we are going to assemble the matrix, any kind of stiffness matrix or mass matrix, we should keep the constant values as a common thing, then only it is very easy to assemble. So finally here we are having a rho a by l, rho a l by 12 into the remaining thing 420 right? After that what we have to do, yes of course, just coming to the point, since the bar is unconstrained, that means no degrees of freedom, that is fixed, no fixed in the, it is not fixed at any one end. So the finite element equation k minus m omega square, k matrix minus m omega square, k matrix m matrix, so Stephen, k minus m omega square into u is equal to p, that is the main equation. So here we are applying the k value and the assembled m value and k value. So we will get the assembled k value here, the assembled m value here. Additionally, this omega is going to be, additionally we are made it here. Okay. Then here the u is changed as u1, u2, u3. Why it is changed as u1, u2, u3? Because in our previous cases we are having how much nodes are there? Node 1, node 1, at here node 1, at here node 2, at here node 3. So that's why here we are having u as u1, u2, u3. As usual, the load p1, p2, p3. So there is no external forces yeah, acting on the body. So p1, p2, p3 is equal to 0. So no degrees of freedom is fixed there. Then we said the determinant of coefficient matrix equal to 0. We have, okay. So this is the thing, and we are rearranging all those things. We will get, and here of course my dears, here very important thing is there, for the simplification purpose they made it here, right? Okay, then here we are rearranging those lines, we are rearranging those things here. One common term, yes, one common term is there, so they are replacing these values by beta square. Okay, right, it's for the simplification purpose only. So in the previous equation can be written as, so that's beta square is available here, isn't it? The beta square is available here. Okay, and we are simply making it, and we'll get another one equation. So finding the determinant, then simplifying it into quadratic equation, then what is that what is that thing is going to happen, right? So with the help of those things we are finding all the values. So beta square, when beta square is equal to 0, omega 1 square is equal to 0, omega 1 is equal, so we are simply applying all over here. Beta square is equal to 1 by 2, omega 1 2 square is equal to, so here we are going to applying in this particular values. Okay, and we will get the different types of answers. So natural frequencies are omega 1 is equal to 0, omega 2 at here, this one, omega 3 is equal to here. Okay, so these are all those things we have to discuss with here. So we are listing out all the results and here. So just keep it up. Omega unit is radian per second. Always whenever you are solving the problem, don't forget to put the unit, my dear. Yes, in the previous problem we didn't have a constraint, that means there is no boundary condition is specially mentioned here, but the another one case is there. Here one of the end, that is the left extreme end, is fixed. Determine the first two natural frequencies of the given bar. The length is 2L, modulus of elasticity E, mass density rho, and the cross sectional area A. So these are the given data. So from these data we are going to find out the natural frequencies. So initially the bar is divided into two equal elements, and here we are having two elements and three nodes are there as usual. we are having the stiffness matrix for element 1. So there is the same procedure which was discussed in the previous class. Then which one is going to be different here? Yes, let us see which is going to be different here. So as usual, for element k1, for element 1 we are having a, for element 1 we are having a k1, for element 2 k2, and we are assembling those things, we will get it. And here next one is the lumped mass matrix for the element 1. So m1 is equal to rho al by 2, right? And here we are having a rho al by 2, right? Okay. And as usual, here we are having a formula is there, okay? And after solving those things, oh, okay, so applying the boundary conditions, so here we are having a very important thing is there. So what is going on? Applying the boundary conditions, u1 is equal to 0, it was fixed. Then there is no forces are available, p1 p2 p3 everything is 0. So u1 is equal to 0 because it was fixed. U2 is equal to u2, u3 is equal to u2. Displacement at node 2 is same, right? So therefore what they are going to do means they are simply applying the values of u1 as 0, u1 as 0, and p1 p2 p3 as 0. So now in the previous equation u1 is equal to 0, so in the previous equation u1 is equal to 0, so neglect first row and first column of k and m matrix, the final reduced equation. So what we are going to do, first row and first column, so we are neglecting the first row and first column, right? So what will happen, let us see. So 2 minus 1 minus 1 1, yes of course, and here 2001, yes. So remaining things are the same. And here what was happened, u is missing, u1, because it was 0. So as usual we are again we are simplifying it, we are finding the values, okay, right? So by finding those values, that is lambda, by using we will get the values of omega 1 omega 2, and two frequencies are available, so these are the natural frequencies. So in the previous problem we had a constraint, that means sonnet is fixed, but the properties are given as numericals, that means alphabets, that means length L, area A. But here instead of that, here if you are giving the dimension, what will be the net effect? So that was going to be discussed in the problem 3. And determine the natural frequencies of longitudinal vibration using two elements of equal length for one dimensional bar as in figure. So just to go through this, they have a single bar, but we have to by using two elements. So the word is very very important thing. Sometimes they may say it as a 3 elements, so be careful about that. Using two elements, okay, using two elements, and it's a 1D bar element, so just keep it as a K matrix and M matrix in your mind. Take Young's modulus, so here they gave the values, Young's modulus value, mass density value, and the length, okay, and the cross sectional area A is equal to 600 mm². So for element 1, L1 is equal to 200, L2 is equal to 200, because it is a 400 mm, so we are making it as a two equal bar, so 200 200 is sharing, and A1 A2 both are the uniform cross section, so that both are also sharing, and Young's modulus is also sharing, mass density is also sharing. So to find the natural frequency of the longitudinal fall, what about the solution? So here the same thing is going to be happened, my dear. K1, okay, AE by L into 1 minus 1 minus 1, so K1 is over, and K2 A2 E2 by L2 as usual, so that is also going to be happened. And after that we got a K2. See, again and again I am repeating, whenever we are going to assemble two matrices, then the common value should be the same, otherwise it will be quite difficult to assemble, that's all. So see here, during the assembly it was very easy. So this is the final assembled K matrix. Now what is that? Next one is the mass matrix, of course. So m1 is equal to rho al by 6 into 2 1 1 2, so m1 m2, so that was happened. And assembling the mass matrix, we will get assembling the mass matrix, we will get these values, and global matrix of longitudinal bar element. So this was clearly stating that global matrix for longitudinal bar element k minus m omega square into u is equal to 0. So my dears, here we are applying the same and applying the boundary conditions. U1 is fixed, isn't it? In our problem, U1 is fixed, so U1 is fixed, so value displacement at node 1 is 0, and U2, U3 we are having the displacement. So as usual, here U1 value is going to be 0. So what is the next thing? In the previous, U1 is equal to 0, so neglect the first row and first column of K and M. The reduced equation is, so first row and first column of the K and M. That's all. So 12 minus 6 minus 6 6, another one is 6.4, 1.6, 1.6, 3.2. Remaining constants are available. So to obtain this solution, we have to seek about that determinant. So we are going to solving as usual by using the method. So what will happen? We will have that lambda 1, lambda 2. So we will get the values of omega 1 and omega 2. So finally we are listed those things. So these are all those things I have to share with you, my dears. If any kind of doubts, you may always ask with me without any hesitation. As much as possible, with my knowledge, I will refer it, or otherwise I will discuss with you. No problem at all. Thank you so much, my dears, for your kind cooperation, and so happy. Thank you.